All right, chemistry, let's take a look at your video lecture for Chapter 11, Section 2, talking about the ideal gas law. In this video lecture, we're going to add yet another law, but it's actually going to be a culmination of the 4 individual laws we've studied so far, so hopefully it won't be that rough for you. At the end of this lecture, I want you to be able to state the ideal gas law, derive the ideal gas constant, and discuss its units. Then, using the ideal gas law, calculate pressure, volume, temperature, and the amount of a gas when the other 3 quantities are known, which is basically if I give you some values, I want you to solve for the other value. Then, using the ideal gas law, calculate the molar mass or density of a gas. This one's going to be new for you guys. We haven't done density calculations since very early in the first semester, so not only is this going to bring back memories, we're going to actually use a slightly different version of the density equation that's more appropriate for gases. And so that might look complicated, but it's that same idea of I'm going to give you terms and I want you to solve for the unknown term is what you'll be doing. Then I want you to reduce the ideal gas law into Boyle's law, Charles' law, Avogadro's law, and then describe the conditions under which each applies. All right, guys, let's get started. Boyle's law states that the relationship between the pressure and the volume of a sample gas, right? We know that. It's pressure times volume equals a constant, meaning it's an inverse relationship. Charles' law states the relationship between the volume of a gas and the absolute temperature of a gas, right? We know that we have volume divided by temperature is equal to a constant. So that's a direct relationship. We have Gay-Lussac's law, states the relationship between the pressure and the temperature of a gas, right? Again, that's an inverse, a direct relationship because we have pressure divided by temperature again. Division means a direct division, direct relationship. And we then last lecture, we saw that Avogadro's law relates the number of moles of a gas to its volume. And so we have these usable equations right here. Again, this table is in your notes. Just to remind you, these are the equations that we have in hand and that we are going to actively use to construct the ideal gas law. So even though this is going to look like a brand new law, it's actually going to be a combination of these 4 things we already know. So I'm saying ideal gas law, ideal gas. In last chapter, we talked about what it means to be ideal. And one of the things I hope we remember is that no gas perfectly obeys all 4 of these laws under all conditions, right? There's no ideal gas. So there's no gas that ideally follows Boyle's law or Charles' law or Gay-Lussac's law or Avogadro's law. Those measurements will all be just a little bit off depending on what conditions you're looking at. But these assumptions, they work well for most gases in most conditions, right? So it's useful. And it's useful because one way to model a gas's behavior is to assume that the gas is an ideal gas that perfectly follows every law. So what you do is you model, you picture, you imagine what an ideal gas would do in a particular set of conditions. And so you have an idea of what ought to happen. And then you observe what the gas actually does. And based on the difference between what you saw the gas actually do and what you predicted the gas would do if it were ideal, from that difference, you can actually conclude quite a bit about the characteristics of that gas. For example, an ideal gas, remember there's no intermolecular forces of attraction or repulsion. Well, an ideal gas, unlike real gases, will not condense into a liquid at low temperatures, right? Once you lower the temperature on a gas, it'll turn back into a liquid. But an ideal gas won't. Because a real gas has intermolecular forces. It has forces of attraction, forces of repulsion at work, right? And so when a real gas condenses from a gas into a liquid, those intermolecular forces are too strong, right? They're too strong, and they actually do cause those molecules to clump back together in what we call a liquid. But an ideal gas, since it doesn't have those attractive forces, won't turn into a liquid. Also, this is also nonsensical. An ideal gas is composed of particles that have no volume. Now, obviously, that's not true, right? But we're talking about ideal gases here.
An ideal gas behaves as described by the ideal gas equation PV equals nRT. There are several assumptions about the nature of a gas that are required for it to behave ideally. A key assumption is that the gas molecules occupy no volume. In a real gas, the molecules have a small but positive volume. Another important assumption is that kinetic energy is dependent on temperature. This means that the molecules are moving at a speed dependent on temperature. Real gases have molecules moving at a variety of speeds. Ideal gases collide like billiard balls and bounce off each other while maintaining their speed. They do not stick to each other or their container walls. Real gases occasionally stick to each other or the container walls. Ideal gas particles are always moving, but collisions that lead to sticking can cause real gas particles to violate this rule. Ideal gases do not attract or repel each other. Sometimes real gases do attract or repel each other. The ideal gas law is written as PV equals nRT. This stands for pressure times volume equals number of moles times the gas constant times the temperature. The gas constant is very important as it relates four measurable quantities: pressure, volume, temperature, and amount of gas. For example, if we take this constant volume box and add more gas to it, the pressure will increase. If instead we have a flexible container and add more gas, the box container will expand. The gas constant must have the units used by the other quantities in the equation. Some examples are R equals 8.314 liter kilopascals per mole Kelvin and 0.0821 liter atmospheres per mole Kelvin. Note that in both examples of gas constant, the pressure unit is different. This results in a different coefficient. Picking the right gas coefficient is important to make sure your units cancel out when doing calculations.
So when using the basic gas laws, we have made use of four measurable quantities, four variables. We've used pressure, represented by P. We've used volume, represented by V. The absolute temperature, which means temperature in kelvins, represented by capital T. And then recently, in the last section, the number of moles, represented by a lowercase n. Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law can be combined into one equation that gives the relationship between all four variables: pressure, volume, temperature, and number of moles of any sample of gas. This relationship is called the ideal gas law. The ideal gas law is represented mathematically below. R is the proportionality constant. The value for R used in any calculation depends on the units used for pressure and volume. So R is also called the universal gas constant. And the value for R can vary. It can vary. Like Robot Lady said, it depends on what units you're using for your pressure mainly, and what units you're using for your volume, a little bit more rarely, but mainly what unit we're using for pressure. So for problems that use, for example, units of kilopascals and liters, if we're going to do an ideal gas law problem, you would use the value for R that is 8.314. Because when you use the 1 atmosphere of pressure, but in kilopascals, the number changes, right? It's not 1 atmosphere, it's 101.325 kilopascals. And so since the coefficient of that standard pressure changes with what unit you use, the value for R is going to change as well. Now, the more common R that we use when doing gas problems just because atmospheres are a little bit more commonly used. More often, the value for R we use is going to be 0.0821 liters times atmospheres divided by moles Kelvin.
The ideal gas law can be derived from Boyle's law, Charles's law, and Avogadro's law. Boyle's law states that, at constant temperature, the pressure and the volume of a gas are inversely proportional to one another. Charles's law states that, at constant pressure, the volume of a gas is proportional to its absolute temperature. From Avogadro's law, it can be deduced that, at constant pressure and temperature, the volume of a gas is proportional to the moles of gas present. Because volume is proportional to the inverse of the pressure, to the absolute temperature, and to the number of moles of gas present, it follows that it must also be proportional to the product of these three quantities. To make this proportionality into an equation, we need to insert a constant. We refer to this constant as the ideal gas constant.
I'm going to interrupt Robot Lady here just to point out that the difference that she's made here. So these first few things that she wrote down were proportionalities, right? This is proportional to this. This is proportional. This is proportional. Right here she's made an equal sign, an equal sign. And so in order to make this not just a proportionality, show that there's a relationship, but actually be able to define that, we have to add a constant. So that's why the constant is added, so we can have this equal sign instead of just kind of this generic proportionality. Back to you, Robot Lady.
And represent it with the letter R. Now, if we multiply both sides of the equation by P and rearrange slightly, we get the ideal gas law expressed in its most common form. The pressure of a gas times its volume is equal to the number of moles of gas times the ideal gas constant times the absolute temperature of the gas.
So the ideal gas law describes the behavior of real gases quite well at room temperature, which is about 21, 22 degrees Celsius, and atmospheric pressure, which is 1 atmosphere, 101 kilopascals. Under these conditions, the volume of the particles themselves and the forces of attraction between them can be ignored, because the overall volume of the particles, the addition to the overall volume of the gas, is so small we can ignore it. It's negligible. Same thing with the intermolecular forces of attraction. It's not to say that there are zero forces of attraction, but it's so small that it's negligible. We can't ignore it, and our overall calculations will not be very far from correct. So the particles behave in ways that are similar enough to an ideal gas that the ideal gas law gives useful results, especially for modeling. Now, as the volume of a real gas decreases, the particles attract one another more strongly. Remember that? That's one of the reasons that high pressure causes a real gas to deviate from ideal gas behavior, because they're closer to one another. The particles attract one another more strongly, and the volume is less than the ideal gas law would predict, right? Because in real life, these gases actually do have forces of attraction, so they'll actually be closer to one another than their normal volume would dictate. So the calculated volume is actually going to be larger than the real volume. Or like we say here, the volume is less than the ideal gas law would predict. So at extremely high pressures, the volume of the particles themselves is close to the total volume. So the actual volume will be higher than calculated. For an ideal gas, the ratio of PV divided by nRT is 1. All right, so PV divided by nRT, so we have that nRT there is actually is a denominator, it's on the bottom, which is represented by this dashed line right here. It's always equal to 1. Real gases deviate somewhat from the ideal gas law and more at very, very high pressures. And so we have pressure here on the x-axis. So we can see as pressure increases to these ridiculous pressures, right, as we get out here, these gases become further and further and further away from this ideal gas line. So let's do a sample problem. How many moles of a gas are contained in 22.41 liters at 101.325 kilopascals and 0 degrees Celsius? Let me ask you, is that STP? Yes, it is. So let's get down what we know. We know that the volume is 22.41 liters. We know that the pressure is 101.325 kilopascals, right? Because that's 1 atmosphere of pressure. It's equivalent. We know that the temperature is 0 degrees Celsius, and we're being asked to find the number of moles of gas present. Now, whenever we do a gas law problem, the temperature has to be the absolute temperature, meaning it has to be in kelvins. So we're going to convert that 0 degrees Celsius into 273 K. Now we can start plugging in to our equation PV is equal to nRT, the ideal gas law. Now, one thing I want to point out here is the problem has given us kilopascals for a pressure. So when we actually go to plug in our R value, right, R right here, we're going to use the 8.314 value because we need to have the kilopascals cancel out, right? So to rearrange to solve for N, we have pressure multiplied by volume divided by the R value, also divided by temperature. Plug all of this into your calculator, you find out it's 1 mole, exactly 1 mole. But that's what we should have because we have 1 atmosphere of pressure, 0 degrees Celsius, which is STP, and look at the volume we have. It's that standard molar volume, 22.41 liters, so you can actually have said without calculating that at STP, this volume of a gas is going to have 1 mole of that gas. Alright guys, that's going to do it for this video lecture. I will see you next period.